Imagine, for a moment, that everything we think we know about space-time, its smooth, continuous nature, how time flows. What if that's fundamentally wrong? What if it's not like a fluid, but built from tiny, discrete atoms?
Right.
Today, we're taking a deep dive into causal set theory, or CST. It's a really bold candidate for a quantum theory of gravity based on this fascinating report you shared.
It is, yeah. And it's compelling because, well, modern physics, brilliant as it is, it rests on these two pillars that, frankly, are kind of at war with each other.
General relativity and quantum mechanics.
Exactly. GR for the big stuff, galaxies, black holes, and QM for the subatomic world.
And they both work incredibly well on their own turf.
Amazingly well, but push them to the extremes, like the Big Bang, or deep inside a black hole. They just violently clash. They predict impossible things, infinities, singularities. Physics breaks down.
So we need something to unify them. That's the big quest, right?
That's the ultimate quest, really.
Yeah.
Finding that unified theory.
And CST steps in here, offering a pretty radical solution by questioning space-time itself. So how does it start to bridge that divide?
Well, the core idea is this. Instead of space-time being this smooth, continuous stage, imagine it's more like a collection of discrete atoms of space-time. Elementary events, you could call them.
Not just a small change, then.
Oh, no. It's a foundational shift. A totally different way to think about reality, and that's where its real power lies, I think.
How so?
Because this discreteness, this granularity, way down at the incredibly tiny Planck length that's like 10 to the minus 35 meters.
Unimaginably small.
Right. It doesn't just tweak the existing physics. It seems to solve that catastrophic problem of infinities and singularities, the ones that plague both GR and QM.
Ah, okay. So no infinite densities if space isn't infinitely divisible.
Precisely. Imagine a universe where our best theories simply stop breaking down at the most extreme points. That's the monumental achievement CST offers, or at least promises.
There's this slogan that comes with the theory, order plus number geometry. Can you unpack that for us?
Yeah, it sounds a bit cryptic, maybe, but it's elegant. The order part is fundamental. It's about causality. Event X can influence event Y. That defines the structure, like a directed network.
So like this happened before that and could affect it.
Exactly. That's the core relationship. Then the number part. That's how you get volume or duration. You just count the elements in a region of this network.
So more elements means more space-time volume.
You got it. And that's how the familiar, smooth, continuous geometry of space-time that we experience kind of emerges, even though at its deepest level, it's actually discrete.
Like looking at a smooth metal bar, but knowing it's made of atoms.
Perfect analogy.
Yeah.
It feels continuous, but it's not. And the numbers are just staggering. A single cubic centimeter by 1 second of space-time is estimated to have something like 10 to the power of 139 causal set elements.
Wow. Okay, no wonder it looks smooth to us.
Right. It's incredibly fine-grained.
Now that discrete idea makes sense for space, maybe. But what about time? You mentioned CST offers a new perspective there, too. How does this atoms of space-time idea change how we think about the flow of time?
This is where it gets really mind-bending. Instead of time being just another fixed dimension we move through, CST suggests it's an active process, a process of becoming.
Becoming.
Yeah, like the universe is literally birthing new space-time elements, new nows, moment by moment. Time unfolds as the causal set grows.
Okay, that is a radical shift from the block universe idea.
It is, but, connecting this to the bigger picture, it might sound like it's just casually upending physics, but it's actually a rigorous, mathematically elegant modification. Think of it like how Einstein refined Newton's physics, not just threw it out.
And crucially, it preserves something called local Lorentz invariance. Why is that such a big deal?
Oh, it's huge. It's a massive achievement for any discrete space-time theory. Basically, Lorentz invariance means physics looks the same for all observers moving at constant velocities. It's fundamental to relativity.
And chopping space-time into bits makes that hard.
Incredibly hard. Most attempts create a sort of preserved frame, like a fixed grid, which violates relativity. CST, remarkably, seems to avoid this. It keeps physics consistent for everyone, even with a fundamentally lumpy spacetime.
Okay, that's impressive. And it makes testable predictions too, right? Let's talk about one of the biggest puzzles in cosmology, the cosmological constant. How does CST help there?
Exactly. This is a potential smoking gun. CST offers an intrinsic explanation for why the cosmological constant, the energy-driving cosmic expansion, is so small.
Unlike quantum theory, which predicts a value that's absurdly huge.
Catastrophically huge,
Yeah.
like 120 orders of magnitude too big. CST, on the other hand, predicts the cosmological constant isn't actually constant, but fluctuates. It scales roughly as 1 over the square root of the spacetime volume V.
So it gets smaller as the universe expands.
Yes, and that fluctuating value aligns far, far better with what we actually observe than quantum theory's wild prediction.
Interesting. And what about black holes? Always a good stress test.
Right. It also tackles the black hole entropy paradox quite elegantly.
The puzzle of why their entropy seems related to their surface area, not their volume.
That's the one. CST proposes that the entropy is directly related to the number of causal links, those fundamental relationship lines that cross the black hole's event horizon. It gives a physical, discrete reason for the area law. It's not just an analogy, it's counting fundamental connections.
That sounds like a neat solution. But of course, no theory is perfect yet. What's the biggest hurdle for CST right now?
Yeah, there are definitely challenges. The main one is often called the manifold problem.
Okay.
It's about how we ensure that the underlying dynamics, the rules governing how the causal set grows, actually produce something that looks like our smooth, continuous, familiar spacetime. Think of it like having a huge box of cosmic Lego bricks. Most random ways you could stick them together would just look like a jumbled mess.
Yeah.
Only very, very specific arrangements look like a smooth shape, or in this case, a spacetime manifold.
So most possible causal sets don't look like our universe.
The vast majority, it seems. So the challenge is finding the specific dynamic law, the rule for adding new elements, that naturally picks out these rare, manifold-like causal sets and explains why our universe looks the way it does. It's a complex mathematical and conceptual problem.
Got it. It's about finding the rules that build the right structure from the discrete bits.
Exactly.
So wrapping this up, what does this all mean for you, the listener?
Well, CST offers this picture of a universe built fundamentally on relationships, causal links, and discrete events. Not just a smooth, passive stage, it's a potential key to some of physics' deepest riddles.
And it really makes you think, doesn't it? If space-time itself is this growing, discrete structure always becoming, how might that change our understanding of things like consciousness, or maybe even free will, things we often tie so closely to the nature and flow of time?
If the universe is constantly birthing itself, moment by moment, what does that imply about the future being fixed or open? A truly mind-bending thought to ponder long after this deep dive.